Hello, and welcome to the Sentinel Innovation and Method Seminar Series. My name is Rishi Desai. I'm an assistant professor here at the Division of Pharmacoepi at Brigham Women's Hospital, and I will be moderating today's session. The US FDA Sentinel system helps to address questions related to safety and effectiveness of marketed medical products. The Innovation Center focuses on developing innovative methods for further advancing Sentinel by leveraging new data sources, building new tools, and enhancing real-world evidence capabilities through advanced analytics. The Sentinel Operations Centers focuses on supporting the FDA in use of the Sentinel Common Data Model and associated modular programs or tools. We launched this webinar series to engage experts and innovators in key areas related to the Innovation Center's master plan and Operations Center's methods work. With that, I'm really pleased to introduce today's speaker, Dr. Nigam Shah. Dr. Shah is a professor of medicine at Stanford University and also the chief data scientist for Stanford Health Care. His research group analyzes multiple types of healthcare data, including EHRs, claims, variables, and so on, to address clinical questions, generate insights, and build predictive models for the learning healthcare system. At Stanford Healthcare, he leads the artificial intelligence and data science efforts for advancing the scientific understanding of diseases, improving the practice of clinical medicine, and orchestrating the delivery of healthcare. Dr. Shah is an inventor of 8 patents, has authored more than 200 publications, and co-founded 3 companies. He holds MBBS from Baroda Medical College in India and PhD from Penn State University and completed postdoc training at Stanford University. So he's clearly a world-renowned expert in the type of things that we care deeply about at Sentinel, including various aspects of using EHR data more efficiently for medical product surveillance. So the title of the presentation today is Ontology-Driven Weak Supervision for Clinical Entity Classification in Electronic Health Records. Before we get started, I would like to mention that your lines are muted. If you'd like to pose a question, please type it in your Zoom question and answer feature. We'll address questions at the end. Finally, this session is being recorded and will be made available through the Sentinel webpage, which can be found at sentinelinitiative.org. So without further ado, I will hand it over to Dr. Shah, and again, thank him for joining us and really looking forward to this presentation.
Thank you, Rishi. It's an absolute pleasure to be here, and apologies for keeping you all waiting for about 6 minutes. The lesson there is not to defer a security upgrade that's pushed by IT ever. I just, deferred it more than that was wise. So the computer is rebooted. Anyway, so we can keep this fairly interactive. Feel free to put in your questions to Rishi. He'll relay them to me. We're in webinar mode, so I see the list of people, but I don't see any faces. Let's get started. So this is sort of a title of a paper that we did, and I kept the same title so as to not change create confusion about the seminar. But my goal is to tell you how we got to this way of viewing data processing from electronic health records, and also share 2 use cases that how this weak supervision idea can help us basically make more sense of all of the unstructured data that resides in EHRs, particularly given the higher interest in real-world evidence these days. So before I sort of launch into anything technical, I'm going to have a few slides of framing. One of the most useful things we have found over the years on doing work on our campus is to always think of a patient timeline. And this timeline view of the data is crucial. Now, if you remember nothing else from my presentation and remember this timeline view and the picture that I'm going to show you, mission accomplished. Like, that's the most valuable thing I can share with you. So the idea there is, on screen is an arrow depicting a patient timeline with the dots denoting when something of consequence happened. Getting diagnosed with COVID, being admitted to the hospital, getting an MRI done, or what have you. Now, depending on where we sit in the healthcare ecosystem, we will see some reflection of this reality that happened. We might see some disease codes, some medication orders, procedures, imaging studies, billing data, some variables and streaming. In this case, I'm showing only streaming, which is the hospital-based version. You might have outside of the health system variable data, genomic measurements. Like this list, probably 50, 60, maybe 80 modalities of information that we could envision being produced on a human being seeking medical care. And then using this patient's timeline, the majority of the work we hear about tends to be what I call intra-encounter, where let's look at an image and diagnose what is present in that image. In this case, cardiomegaly from Czechsnik's project that Kurt Langlotz, Matt Lunger, and a few others did. Obviously, a lot of activity in the billing side. And then just one other vignette, which is looking at all of these electrical signals continuously measured on a human being to then anticipate some impending deterioration, a requirement for resuscitation, things like that. And of course, you can imagine lots of other situations, going as far as to using all the data, maybe even the past data at a given point, available at a point in time, to then do either some sort of risk stratification or recommend some treatment. And the risk stratification boils down to either solving a classification problem, figuring out what the patient has, or solving a prediction problem, which is about forecasting something that will happen but has not yet happened. Now, granted, this is a very patient-centric view of the information. And in the Sentinel project, the unit of analysis is usually a drug and its association with some outcome. But that is computed from this underlying individual patient timeline. So this patient timeline manifests to us as sort of some hideous looking interface. This is just something I pulled off the internet, but underneath is this timeline object. And we have these for millions of patients. The billing data available from Trove and RBM Market Scan, from Optum, very familiar. Lots of you, I would imagine, use them. The Sentinel data sets, similar in nature. But there's additional information in the EHRs that doesn't always propagate into the billing records. But no matter which way you're coming from, billing or EHR data, at some point, we have to convert this timeline into a data matrix. Now, what I'm showing you is a tensor. It has the time dimension sort of spelled out, but often we see it in a compressed form where someone has already made decisions about how the time dimension is going to be handled. And then there's lots of decisions to make about the source and choice of features, including text, about handling of time, which I alluded to, about defining this thing, which in the informatics community is called electronic phenotype, otherwise also called health outcomes of interest, or defining your exposure, or the definitions of the various aspects of your PCOT definition. A good way to think of it is that what are the necessary and sufficient conditions for what you need to see in the electronic record for you to believe that an exposure or an outcome happened? I mean, that's sort of the gist of electronic phenotyping. And then we need to pull in the patient records and build a cohort, get it into this nice data frame upon which we can do some analysis. So lots of decisions to make. Text is one source. And I really want to stress this point, that when we start talking about text mining, text processing, natural language processing, that worldview comes with its own unique goals, which is to understand the language in the document. Whereas our goal, at least my goal, is something quite different, which is text is one source from which I can create features that go into my patient feature matrix. And that mind pivot opens up new avenues of dealing with this unstructured information. All right, so the core themes, we'll make a distinction between processing of text versus natural language processing. And sort of my quip is, for those of you who've seen EHR language, it is not natural by any form or means. Then why would we be applying natural language processing? I mean, it's kind of a tongue-in-cheek joke, but to illustrate the point that our goal is to get something out of the text and not necessarily process that as natural language. Then there's this notion, this necessity of handling knowledge graphs, ontologies, terminology, structures, whatever you want to call them. And all of that feeds into this final bullet of ascertaining whether the patient had an event, an exposure, an outcome or not, and when was that. And we can choose this task by focusing just on the document, or we can choose to do this task as a classification problem, where the text extracted content is just one element, one of many elements on the patient timeline. And that's what we're going to be focusing on today. So just wanted to set this broader frame of reference. All right, so let's look into the handling of the text. This is sort of a cartoon note that I typed up myself just to illustrate this, two different ways of thinking about text processing. So on the left is the original document, completely fake, I just typed it up. On the right at the top is the usual way people think of processing textual documents, particularly clinical documents, which is that let's find and redact PHI so that on what remains, we can apply natural language processing. What I want to sort of point out is this lower right, which is if we use all the terminology information at our disposal, and we believe that most medical things are covered in some terminology somewhere, we can take this complementary view that says, I'm going to keep medical terms and leave everything else behind. And the graphic on screen sort of shows you for that same text note what happens. And as you can see, you kind of get de-identification for free. And if your goal is to just engineer features, this keeping medical terms has all of the necessary information. And we'll spend a couple of slides on sort of double clicking on that, particularly given that some of our work from the 2013 timeframe about using this kind of medical information, just keeping these words around and then using them for drug safety surveillance has sort of resurfaced again as of being of interest. So let's spend a few minutes on this side, and then we'll go back to the weak supervision applied to the top side of the document. Okay, so simple text processing, 2 slides on what it can do for us. So I'll just show you pictures and walk you through them. So let's say we have some input text. This is again a fake note. And we're going to do some text processing, which includes understanding of knowledge graphs. And I'm only showing you one with a cartoon of drugs where we can have a section of the knowledge graph that, say, spans oral antihistamines in this example. We definitely have to do something about recognizing negation and recognizing context in the form of, is this about the patient or somebody else? Is it about now or a historical mention and something and things like that? This processing then yields a data structure, which is shown in blue. It's basically a bunch of numbers and which word appeared where in the document, literally storing a bunch of integers. Like, it's very hard to interpret, so I've sort of unfolded it into a human readable version where we've kept all the medical terms. What was negated is shown in red, and then we just remember what was said in which document when. We defer binding to any medical concept. So if you see a word like stroke, we don't try to disambiguate, is it heat stroke, heart stroke, or whatever. Just remember that we saw the word stroke at position this in this document. So let's call that thing an index of term mentions. And then we just store it. When we have a question, let's say about juvenile idiopathic arthritis and the incidence of uveitis in those patients, we first go to knowledge graphs for diseases, drugs, procedures, devices. And then we get a list of codes and words that, to the best of our knowledge, we believe are necessary and sufficient for us to conclude that a person had, in this example, juvenile idiopathic arthritis. We can do the same for uveitis, we can do the same for idiopathitis, for drug exposures, what have you. And then we count present positive mentions that are about the patient. And that gets us this patient feature matrix that then feeds into all downstream analyses. And the citation below is the paper where we applied this idea for drug safety surveillance. So does this work? We think it does. And we did a head-to-head comparison where we took about 1,200 documents from the 2008 I2B2 NLP challenge and put it through our system, which is highlighted here as the annotator, and 2 other natural language processing systems. And for benchmarking, we basically participated in the 2008 challenge, like in silico and in 2010, so not actually as the challenge, but we kind of did the test for ourselves. And you can see the performance is hard to tell apart. By and large, about the same in benchmarking. Had we taken the challenge, applying the same metrics as the challenge applied, we would have come in about second or third in the challenge. So I said, all right, that's great. Let's do a functional evaluation. So we took the annotator, we took the reveal the best performing system, which was at the time based on Medley. We do the processing, we create our patient feature matrix, and then we ask questions that the answer we get about the safety profile of silastazole, is it the same answer or a different answer, whether we use natural language processing or simple text processing? How different is our ability to detect drug-drug interactions? And what we're looking at is the UROC. The color tells you which was the text processing approach used. Same thing for the plot below. And then we attempted to build a classifier for just detecting which drug is used to which disease. And then, of course, we know the gold standard. Again, very little difference in performance. And that sort of clued us into using simple ways of processing text for the purpose of making sense of electronic health records. All right, so I'll just park that, and then now let's step back out into the processing of the entire document after PHI has been redacted. Of course, trade-offs, you do get more signal if you do that, but there's also more agony in accessing those documents because you can't really prove it's de-identified. So most institutions, including ours, tend to treat it as high-risk data. But once you get access to that, let's see what we can do with it. So in 2020, which is when we started down this weak supervision path, the state of affairs for clinical concept recognition, and this is from this review, is it was largely based on rule-based extraction or manual feature engineering, required a lot of hand-labeled training data, which the I2B2 challenge was one of the first pioneers in providing early on. But otherwise, there were not that many labeled data sets. And for those that are available, we don't have access to the source. So you're kind of stuck with what's provided to you. And then obviously a lot of PHI considerations when sharing these labeled data. So not many hand-labeled data sets, but lots of free ontologies. And for those of you who are familiar with the BioPortal and the National Center for Biomedical Ontology, now the CEDAR Metadata Center, we can get these things via APIs and use them for creating automatically generated labeling functions. So that's this idea of weak supervision. So the goal there is, let's take a document. So that's the thing in the box. And we want to go to the terminologies, perhaps run an exact match of some sort. And so that's the text processing bit from the simple text processing conversation we just had. And we want to mark up the present positive mentions of those words. And then we want to rely on these ontologies to tell us what kind of entity that is. So aortic stenosis, in this case, is a disease. The ones and zeros are for disease. And then what are their synonyms and acronyms? In this case, aortic AS is a synonym for aortic stenosis, MR for mitral regurgitation. Now, of course, it's not perfect. There are things like MG, which could be magnesium milligram or myasthenia gravis. But because it has three meanings, we can know that up front just by analyzing the knowledge graph of the ontology and then suppress those strings. For the rest, we just automatically label the note instead of having a human highlight mitral regurgitation and tell us that it is a disease. So that's the intuition. And how well does it work? So if we just take the majority vote, because these multiple terminologies might disagree, how good are we at recognizing chemicals, diseases, disorders, drugs, negation? And that's what you see in this column right here. So that's sort of the baseline. That's the majority vote, right? We're not doing anything fancy. We can then learn a model, just based on the labeling functions. That does a little bit better. Or we can do this thing called weak supervision, where after learning a model, we manufacture fake data, so to speak, as in based on the labeling functions and its prevalence, we create more instances of the kinds of things we've seen, and then we train on that. So that's this weak supervision based, and you can see you get a little bit of further boost in performance. And on the right is what do you get if we have the hand label data, full supervision from manually annotated examples, and this is state-of-the-art report in the literature. Net, by this weak supervision business, we can get to within 4% of hand labeled performance for quote unquote for free. So that's sort of the take home here. So what do we do with this now? One of the applications we had, 2020, March 16th, the world changed for all of us. We said, could we be using presenting symptoms to prioritize who should be tested for COVID-19? This was when tests were in short supply, PCR testing wasn't as widely available. So we took the daily feed of all documents, time-stamped edits in our emergency department. We just used the first 30 minutes of those edits. We did this automated labeling based on that. And we had some small amount of label data, which we then used to train this model, which produces a large number of quote unquote fake training data. Based on that, we attempt to then categorize new patients into, do they look like a COVID patient or do they have something else? Long story short, very early on, we're able to say we will not be able to discriminate respiratory viruses from symptoms alone. Of course, this got buried in the millions of papers that got published. And early on, we said that is not a productive exercise. It will not work. And in hindsight, we kind of know that it's not really possible to distinguish COVID based just on symptoms. The other useful thing this pipeline was able to do, this was about 2 F1 points better than just doing a baseline. The other two things this enabled is that we were able to share this through support from the Bill and Melinda Gates Foundation with the Carnegie Mellon Institute's Delphi team's COVID-Cast project, which was using essentially the prevalence of these symptoms along with signals from web searches and so on in order to forecast the disease burden in certain areas of the US. So fast way of taking unstructured data from EHRs and putting it to some good use. The other example that I'll share, and then after that we'll open it up for questions, is of doing medical device surveillance with EHRs. So a lot of you are familiar with the drug safety work, and you might also be familiar with the MOD database for devices, which is kind of like the FAERS for drugs. And at one point, there was this investigation that got released publicly as the implant files by the International Association of Journalists, Medical Journalists, basically arguing that medical devices also have the needs for being surveilled just like we do drug surveillance, and it's typically much harder than doing it for drugs. And we said, all right, could examining the unstructured EHR help? So what we're seeing up top is a patient timeline where someone has a primary total hip arthroplasty surgery, and then there's a bunch of documents, and at some point they might end up having a revision surgery. And we want to be able to detect which kinds of implants are associated with higher or lower rates of revisions and other complications. So we have these documents. First pass, we just use the simple text processing based approach using existing dictionaries from the UMLS and the foundational model of anatomy. We then do the same trick of creating labeling functions based on term mentions that are detected across all of these terminologies. And after that, we're able to identify, without having a lot of manually labeled training data, and a set of relationships, such as this particular patient had a left hip, which was this Depoy model, had a loosening, and then also had metallosis detected in the patient's record later on. And the citation below is the article where this figure is from. And so we said, all right, now let's use this in order to identify, are there devices for which there are differing rates of complications that are documented in the EHR. And the goal was to essentially supplement a joint implant registry. So on the left is sort of the anatomy of the hip joint implants that we looked at. They have all these different parts: femoral head, stem, acetabular component, what the liner type, what it is, and so on. All of that needs to be detected because depending on the material composition, the complication rates might differ. And here's the implant files thing that I mentioned. And so we have a bunch of documents, we push it through this text processing systems, and we find all of these things happening, such as in the left hip, there was pain, this was the implant type, there was some loosening, and there was pain. If we zoom in a little bit further, we can detect relationships such as, this acetabular component had a complication and then had to be replaced. And that markup is kind of now overlaid onto the document and also extracted for further analysis. Of course, we had to do a small set of manually labeled data just to evaluate our performance and convince ourselves that this idea works. The rest of the training set is programmatically labeled. And then we use that to detect occurrences of complications, as well as the kind of implant and its subcomponents. This is just a geek out slide of what the text processor provides based on words that are found that are directly from the existing knowledge graphs and ontologies, and then this labeling functions that operate some logic on top of these and then assign things into, was this negated, was it historical, is it a complication, what body part it is, and so on. And then automatically we can label a very large corpus as opposed to manually having to do that. The punchline there is that we get a big boost in recall. We can detect 6 times more complication events than we would have detected with coded data alone. That's sort of the bottom line. Now, of course, it doesn't work universally. As you might see in radiographic abnormality, we actually take a hit and performance goes down. But for the most part, we see a higher ability to identify both implant complications as well as the site where the patient had pain. All right, so to wrap up, think of the patient timeline object. On that timeline, we have documents that are one part of the complete repertoire of information. And as we think about processing those documents, I would encourage you to think about processing them in the context of the rest of the information in the patient timeline. So for example, if you see a word stroke, but it's a pediatric medical record and the date of admission is August, and you see other words like ice packs, it's heat stroke. Like, you don't need much more fancy NLP to disambiguate whether it's heat stroke or cerebrovascular stroke, for example. So I'm going to show you a very complex looking hand-drawn slide and then break it up into chunks. So there's a whole bunch of data sources on which we can do a bunch of text processing. And I've walked you through sort of this one example and then this other example. And then there's different ways of handling the text. But the key is the way we handle the text and the way we handle the knowledge graphs and the way we ascertain whether something happened, the phenotyping strategy. Those are sort of the 3 big buckets of work, which I've highlighted as these yellow boxes. Those 3 things need to be then orchestrated. Your text processing, your knowledge graph handling, and your phenotyping strategy into a search that then allows you to operate on top of these patient timelines to produce a patient feature matrix that can be used for all sorts of things. And I've shown you an example of looking at complications of medical device implants and for symptom surveillance for COVID. And I think that is my last slide. Here's the wonderful team that helps me do all of this and makes all of this exciting work possible. This is pre-COVID. It's a late February 2020 picture. The majority of people in this picture have actually graduated, but this is the best picture I have. And the work that I've been showing you is this person here, Jason Fries, is kind of the lead, supported very strongly by Alison Callahan. They were sort of the main two people doing the work on the medical implants. And then Ken Jung did the head-to-head comparison of simple methods versus fancy methods. And more information at this URL, and I'll stop here.
Great, thank you, Nigam. That was an excellent overview of all your work over the years and very methodically done. So really appreciate you taking the time today. So I'd like to remind the attendees that this floor is now open for questions, and you can type your questions in the Zoom question answer feature. So as people are thinking of questions, Nigam, I can probably start with one of my own. So the weak supervision paper, or the method that you discussed there, is very interesting. And I was wondering if you had thoughts on how would you do this in a distributed network where you have data residing at multiple sites, and you may actually, so typically we have thought of phenotyping algorithms as developing at one side and then implementing at the other side, knowing full well that the other side may be not as well performing. However, in this situation, it seems like because a lot of this is automatable, you may be able to actually do site-specific training. So I was wondering if you have been thinking about this or have examples to share.
So we have not been pushing this further, mostly because we got interested in other things. But your intuition is spot on. We did do one study where we looked at sharing the phenotype algorithm, even a machine learned classification algorithm directly, versus sharing the pipeline so you can relearn the algorithm at the local site. And relearning always works better at the local site. So your intuition is spot on that, if we solve the problem of how do we share this with all sites so that everybody can learn locally. And as I often joke with Mike Benzina, we say like all models are like politics, so they're all local. We shouldn't expect them to generalize. So we have created all of this sort of package, all of this pipeline into a software package. So underlying technology is built by Chris Ray's team, who's a professor in computer science. The first iteration of that was called Deep Dive, and the second iteration is called Snorkel. And Snorkel is available under a very permissive license. So we took Snorkel and we took ontologies from UMLS, created a whole bunch of labeling functions, which we have tested and validated, and released that as a software package we call Trove, Trove. And so Trove is basically ontologies, labeling functions, and the Snorkel library, text processing library combined so that people can use this at their own sites. And it's freely available from our GitHub repo.
That's great. Thank you so much. And then it looks like there's one question that popped up. So a question from anonymous attendee. Have you had any experience running your phenotype pipeline using HL7 data? It could be useful for automating timely assessment of device safety.
We have unfortunately not dealt with HL7. That's basically being a little bit spoiled that we have a good research data warehouse, which is a lot easier to work with than HL7. So unfortunately not. I've not worked with HL7 data. Okay.
Any other questions? Feel free to type them, and we will be happy to address those. Because we have some time, I can also ask one more question. So Nigam, it sounded like a lot of the work that you have done is mostly focused on the text mining of exposure and outcome, at least for the hip fracture example that you were showing. I was wondering if you had also experience or other lines of work which may be geared towards putting together a bunch of different types of data sources and using all of that type of information to get at different variables or different measurements through those sources. So just making just going back to the first figure that you were showing, there are various modes of data collection, and I was wondering if there is a repository at Stanford that you have developed, just combining all of those sources into the one central thing.
So in terms of the repository, we do have what we call our star data lake. Stanford Translational Research Data Warehouse, led by Somali Datta and Todd Ferris. And basically, if you go in with the MRN or an identifier, you can pull in the patient's codes, their documents, their waveforms, their imaging data, and all of that. It's not in one database, and hence the data lake word usage. And the storage profiles of all of these data types are also quite different. You can't, it's really hard to put waveforms into relational database tables. And so once you have a list of MRNs, you can then go pull in everything about them. Now, in order to create the list of MRNs that are of interest to you, and to create them by operating on this patient timeline object in its entirety, minus the images and waveforms, for example.
Right.
We've released a search engine called ACE. It's open source. It's in the publication is also open access. It is in JAMIA, and ACE works off of patient timelines as opposed to tables of patient information. For those of you with computer science background, databases are relational algebra. This timeline business is interval algebra, also known as Allen interval algebra. So we've created software that allows you to operate on time intervals in order to create your definition of what constitutes an outcome or an exposure, by combining laboratory test results, presence or absence of codes, and mentions of words in textual documents.
Okay, great. That's very helpful. Thank you. I don't see any other questions popping up, so we can give folks maybe a minute to think.
I mean, I can pull up the ACE website, and it gives a nice, or the paper, sorry, and then that will give a nice intuition of how this works. So just give me a sec, and there we go. So this is the journal article that we alluded to just a few minutes ago. And if I jump straight to the image, it will open in a new tab. So here we're looking at 50 patients. We're looking at their timelines, and one of them is highlighted, the one that's in highlighted in light green all across. And for that one patient, we can see intervals where certain conditions are true. So in orange, for example, where my mouse cursor is, there's this no history of stroke. So in this particular timeline, that thing, no history of stroke, was true from whatever time frame point here to here, and at that point they had a stroke. And so from that point on, no history of stroke is no longer true. Similarly, there are intervals where they were diagnosed, where the constrained diabetes and then treatment with glipizide was true, and that is these two intervals here. Having glipizide and then getting a stroke, that's true in these pink intervals, and so on. And then you can see office visits and telehealth and so on. So that's like this particular part where my cursor is one patient record. The top panel is all 50 patients, and you do have to learn this hideous syntax in order to operate over this patient timelines.
Yeah, that's amazing. Thank you for sharing that. All right, well, in case of no questions, we can thank Nigam for his excellent presentation and really his amazing work over the years that has informed so much in the informatics community and how we use EHRs more reliably. And thank you, Nigam, again. And yeah, if there are any more questions for Nigam, feel free to send it to us, and we can communicate with him. But again, wanted to thank you, Nigam, for your time, and I will definitely see you around.
All right. Well, thank you for having me, and it's always good to give time back to people. 15 minutes back in the day is awesome.
That's great.
So thank you.
Thanks.
Bye.
Bye.